Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I will continue to cover this topical MCQ on topic 4, which is on states of matter, as well as the gas laws that involve all those Charles' law, Boyle's law, Avogadro's law, as well as the ideal gas equation. So in this first question, it's saying that chlorine does not behave as an ideal gas at room temperature and pressure, but you want to become more ideal. If you want to become more ideal, you want to obey the assumptions of the ideal gas more and more. So we want to obey the assumptions of the ideal gas more. And the most important assumption of ideal gas is about negligible intermolecular forces. So if we are at lower temperature, then they are closer together, then their intermolecular forces are not as negligible. So we are not looking at low temperature, we are looking at higher temperature, so that the chlorine molecules are further apart, then their intermolecular force between them are as negligible as possible compared to room temperature, for instance. Yeah. In terms of pressure, if I make the molecules closer together by applying high pressure, then they are going to be closer together and they will not have negligible intermolecular force, compared to if I decrease the pressure, if I lower the pressure, then they will be further apart. When they are further apart, then they won't have they will have more negligible intermolecular forces. So I'm looking at low pressure and high temperature. So these are quite some of the common questions that always come up, whether in this form of values or whether as these kind of trends, where they ask you to pick up the trend. All right, so just thinking about the assumption of ideal gas, thinking about the most important assumption, thinking about whether you're making them closer together or further apart would have enable you to answer this kind of question easily. This next question is about identifying the different elements. So these are elements, and looking at it, I think you can tell that element X is going to be simple molecular because of the very low melting and boiling point. And also you can tell that at room temperature and pressure, so at room temperature and pressure, which is 25 degrees Celsius or 298 Kelvin, this thing X is going to be a liquid. It's a liquid, so at room temperature and pressure. And the way we can tell is because at 25 degrees Celsius it's higher than the melting point, so it will have melted, but it wouldn't have boiled yet because you are still below the boiling point. So it's a liquid, and X is Y is a solid and Z is a solid. Out of X, Y, and Z, you have bromine and you also have iodine, but only bromine is a liquid at room temperature and pressure. Iodine is a solid, is a gray black solid at room temperature and pressure. And iodine is part of your case study under states of matter, where you should know the structure, the appearance, etc., etc. So we can cross out C and D, so we're just left with A and B. In terms of aluminium and sodium, you should probably be aware that sodium, so to group 1 metals, okay, especially lithium, sodium, and potassium, they float on water. So if you have seen the reaction of sodium with water, you will know the sodium floats around the water, and then it's a very vigorous reaction. It starts to catch fire. So the density of water is 1.00 gram per cm cube. So the fact that you are 0.97, so you're less dense than water, you will float on water. So that's actually a property of sodium. And in terms of Z, so if Z is magnesium, magnesium doesn't float on water. And then we also know that magnesium has a stronger metallic bond than sodium. Okay, so magnesium has stronger metallic bond. And you can think back on your last topic, what factors make it a stronger metallic bond? Mg2 plus is smaller than Na plus. Mg2 plus can delocalize 2 valence electron versus 1 valence electron for sodium. And what's the other one I was going to say? Number of electrons you can delocalize. the size of the cation as well as the charge of the cation. Mg plus 2 versus Na plus 1. Higher charge, smaller size, delocalized more valence electron. Therefore, you can have stronger attraction with your sea of delocalized valence electrons. So magnesium has a higher melting and boiling point, has a stronger metallic bond than your sodium. Moving on to the next question. So this looks like an ideal gas calculation kind of question. This is ethene gas, so it's C2H4. If you work out the MR of C2H4, that's 12.0 times 2 plus 4 times 1.0, that's 28.0. And then we have PV equal to nRT. So the N is equal to the mass over the MR of the gas, because this is the mole of the gas. Alright. So if you rearrange the equation, so PV equal to M over MR RT, V is equal to MRT over PMR. I would not advise you putting in all the values in. Instead, work out the value on the side. So that's 0.656 gram. R is at 0.314 joule per Kelvin per mole from your data booklet. Do you use at 0.314? Let me have a look. You use 8.31. Okay, so you don't use that high accuracy. Yes, use 8.31. What else? We have temperature, which is given in 30 degrees Celsius. So we have to convert that into Kelvin by adding 273. So they gave me 303 Kelvin. My pressure is given as kilopascal, so I have to convert that to Pascal, because 1 Pascal is equal to 1 Newton per meter square, and that is the standard unit you will need in your ideal gas equation. And this volume that you calculated will be in meter cube, because we are all in SI unit. Alright, so that will be in meter cube, but they want it in cm cube. I will worry about that later on. Let me just work it out first. I just want to make sure that you know the unit of volume in ideal gas equation is in meter cube. So put in all that into your calculator. I forgot the MR is 28. So that gave me 4.937 times 10 to the power minus 4, that's meter cube. So 1 meter is equal to 10 square cm. If I cube both sides, so that means I put the whole thing in bracket and I cube both sides. Whatever I do on the left, I do on the right throughout. Okay, because this is the meaning of the term equal. So that gives me 1 meter cube is 10 to the 6 cm cube. Therefore, I just multiply the whole thing, because it's in meter cube, I multiply the whole thing by 10 to the 6. And I got my final answer is 494 cm cube to 3 significant figure. So there's the answer B there. So I guess you're a bit lucky that the option given didn't have this 10 to the minus 4, because sometimes students can get confused and then they just pick the one without thinking about the units. All right. So in this next question, I had to reedit the video a little bit, because one of you guys, one of the viewers, actually raised up a mistake that I made with these particular questions. So let's try and analyze the question all over again. We can see that with the melting and boiling point, this tells us the structure and bonding. So these are very, very low. These are negative numbers. So these are low. Low melting and boiling point. That can only indicate one thing. It has to be simple covalent structure or simple molecular structure, which all of the options for R is like that. Now, having a look at these are very high melting and boiling point, which suggests giant structure. So all of these are giant structure except for SiO2, which is giant covalent structure or giant molecular structure. But we have conductivity as a solid, as a liquid, as well as an aqueous solution. So we know that here it doesn't conduct when solid, but it conducts when liquid. And this one doesn't conduct when solid, but conducts when liquid. we know that SiO2 has no free electrons, so it will never conduct even when it is solid or liquid, or in fact it doesn't dissolve in water at all. As you will know, in general periodicity, as part of period 3 oxide, SiO2 is also insoluble in water. Okay, but the fact that we have this thing here where it says insoluble, meaning to say it doesn't conduct in aqueous solution, does not straight away say that it's SiO2, because of this thing here, which is very important. It says that it conduct when liquid, therefore it cannot be SiO2, because SiO2 does not conduct even when it becomes a liquid. Therefore, we're left between option A and option B there. So MgO is settled. So between KCl and NaF, well, let's try and not think about that. Let's try and go straight to NH3 and C2H5Br. NH3 is a gas at room temperature and pressure, which is 25 degrees Celsius. And then these are halogenal alkanes. These halogenal alkanes are liquid at room temperature and pressure. So looking at the boiling and melting point, this goes back to the year 9 states of matter topic. So if this is minus 119 for the melting point, and it is 39 for the boiling point, where is our 25? 25 is going to be somewhere in between if there's the temperature in degrees Celsius, and therefore in between the melting and boiling point, you are going to be a liquid in between your melting and also boiling point there. Okay, so we know that it cannot be ammonia, because ammonia is already a gas at room temperature and pressure, so the answer cannot be ammonia. Therefore, there can only be one possible answer, which is option B there. This is the last question of this 5-question topical MCQ series. It's another ideal gas calculation. The temperature is in 30 degrees Celsius, so convert to Kelvin. This is in meter cube, so it's all good. This is in gram. This is oxygen gas, so make sure you use O2, which is 16.0 times 2, so that's 32.0. Assuming it behaves like ideal gas, what's the pressure? In this ideal gas equation, the pressure is in Pascal or Newton per meter square. You have a kilopascal, so just make sure you're aware of that, yeah? So PV equal to M over MR RT. Mass over MR give you the mole of the gas. You want the pressure. I will rearrange the equation first, and then I write down what I need on the side. R is at 0.31 joule per Kelvin per mole, which is from your data booklet. The T has to be in Kelvin. So at 273, you're going to get 303 Kelvin. Your V is already given in meter cube, so that makes your life easy. Your MR is for the oxygen gas, so it's not for oxygen atom. It's 32.0 gram per mole. So your pressure, based on all this, will be calculated in Pascal or in Newton per meter square, as I mentioned, because there's the unit in the equation. So I got 10,791, that will be in Pascal. So if I convert it to kilopascal, that will be 10.8 kilopascal to 3 significant figure. Alright, so this is the end of this 5-question series in this states of matter and the gas laws topical MCQ. I'll see you in the next video. Don't forget to click the button on the bottom right, subscribe to the channel, share the channel widely with friends, your social contacts, whoever else you think these videos, these tutorials might be useful for, and thank you for watching.